All right, so let's summarize the cases so far. Summary so far. So we mentioned that our goal is to solve y double prime plus p of x times y prime plus q of x times y equals 0. And p of x and q of x, we assume they're continuous functions in order to guarantee existence and uniqueness of solution with two initial values. If you have two initial values and p of x and q of x are continuous functions, then we are guaranteed to have a unique solution. Now, the simplest case where p of x and q of x are continuous functions, basically that we want to consider as our starting point, is if p of x and q of x are constants themselves, constant functions. So simplest case, p of x equals b and q of x equals c, constant functions. And so we will have y double prime plus by prime plus cy equals 0. Now we solve this equation if b squared minus 4c equals 0. We saw that y1 equals e to power minus b over 2x, and y2 equals x times e to power minus b over 2x. And y, the general solution will be c1 y1 plus c2 y2. Now in the next case that we want to consider, again, we want to still consider the constant coefficient case. So in the case that the p of x and q of x, the coefficients are constant functions, we naturally call this type of equation constant coefficient function, constant coefficient equation. And so we already solved it in the case that b squared minus 4c is 0. Now in the next case, if b squared minus 4c is bigger than 0, or if it's less than 0, how can we find the solutions? So first, so let's consider y double prime plus by prime plus cy equals 0, and b squared minus 4c is not equal to 0 at this time. When I say it's not equal to 0, it naturally means either it's positive or negative. We'll see how to find the solution in each case where it's positive or it's negative. But for now, let's start with not equal to 0. And let's see what the calculation tells us. So again, let's consider our first solution. In the form, or let's say our solution or solutions. Let's see how many solutions we get. Our solution or solutions in the form y equals e to power rx. And here r is a constant. But the previous case where we considered e to power rx, it gave us one solution, and then we had to find the second solution according to the algorithm that we derived before. But we found one solution in previous case because the corresponding algebraic equation, the quadratic equation, was an equation with discriminant 0, and it had one root. So that's why we got one solution. But as we will see in this case, we will have a quadratic equation with two solutions this time. And therefore, both the solutions this time can be written in this form. So I will show you how we can do this and find write both solutions in this form. So let's start with y equals e to power rx. And then we will have y double. What will be y prime? Y prime will be equal to r e to power rx. Y double prime will be equal to r squared e to power rx. And we know that y double prime plus by prime plus cy equals 0. So that means r squared e to power rx plus b r e to power rx plus c e to power rx equals 0. I can take e to power rx out as a common factor. Then I'll have r squared plus br plus c equals 0. So then I'll have r squared plus br plus c equals 0, because again, exponentials are always positive and non-zero. So r squared plus br plus c will be 0. And now this is a quadratic equation. It will have two solutions this time. So it's a quadratic equation with two solutions. What are the two solutions? R equals minus b plus minus root b squared minus 4c divided by 2. So you may say here, if b squared minus 4c is positive, we will have two solutions. But if b squared minus 4c is negative, shouldn't we say that we have no solution? But if b squared minus 4c is negative, we have no real solution, but we still have two complex solutions. So note, if b squared minus 4c bigger than 0, two real solutions. If b squared minus 4c less than 0, two complex solutions. So let's set R1 to be minus b plus root b squared minus 4c divided by 2, and R2 equals minus b minus root b squared minus 4c divided by 2. So then we found two values for R, R1 and R2. So that gives us two solutions, because remember the solution is of the form e to power Rx. But we found two solutions for R, R1 and R2. So that gives us two solutions for Y, Y1 and Y2, which are e to power R1x and e to power R2x. So this gives us two solutions. So this will give us two solutions. Y1 equals e to power R1x and Y2 equals e to power R2x. So we found two solutions for our equation. Y1 equals e to power R1x and Y2 equals e to power R2x. But still we need to check that Y1 and Y2 are linearly independent. Note that Y1 and Y2 above are linearly independent. Why are they linearly independent, or how can I check that they are linearly independent? So because here I have two functions, one way to check that they are linearly independent is using the definition of linear independence, like C1 Y1 plus C2 Y2 equals 0. And then I have to conclude that C1 and C2 must be both 0. Or I can check that Y1 and Y2 are not scalar multiply of each other, because there are just two of them here. If I check that they are not scalar multiply of each other, that means they are linearly independent. Or I can use Wronskian. In my experience, I think many students are more comfortable with Wronskian because just a simple calculation of determinants, if that determinant is non-zero, not constant function 0, then that means the functions are linearly independent. So note that y1 and y2 above are linearly independent. We can check this. Using Wronskian. So W of y1 and y2 is equal to determinant y1, y2, y1 prime, y2 prime. So that's equal to determinant e to power r1x, e to power r2x, r1 e to power r1x, r2 e to power r2x. And just use the formula for determinant, this times this minus this times this. That gives me r2 e to power r1 plus r2 times x minus r1 e to power r1 plus r2 times x. So that's going to be r2 minus r1 e to power r1 plus r2 times x. And this is not 0 since r2 minus r1 is not 0 because r2 and r1 are not the same number. R1 is minus b plus this number, R2 is minus b minus this number, and this number is non-zero. That's important assumption. Remember, we were assuming that b squared minus 4c is non-zero. So R1 and R2 are not the same. So R2 minus R1 is not 0. Exponential always non-negative. Exponential always positive. So non-zero. This is also non-zero. The answer is also non-zero. The answer is in fact non-zero for every x, but even if the answer was non-zero for one value of x, still it would be enough. Still it would mean that the functions are linearly independent. So this is not equal to 0 for every x. Recall that if W of y1, y2 is not 0 for one value of x, then y1 and y2 are linearly independent. So here we can say that y1 and y2 are linearly independent. So that means the general solution of y double prime plus by prime plus cy equals 0 with b squared minus 4c not equal to 0 can be written as follows. Y equals c1 y1 plus c2 y2. We found two linearly independent solutions for this equation. So we can write the general solution as c1 y1 plus c2 y2. So that's going to give us c1 e to power rx plus c2 e to power r c1 e to power r1x plus c2 e to power r2x. And here r1 is minus b plus root b squared minus 4c divided by 2, and r2 equals minus b minus root b squared minus 4c divided by 2. So if b squared minus 4c is positive, remember we're assuming that b squared minus 4c is non-zero, which means either positive or negative. If b squared minus 4c is positive, we already have two real solutions here and the general solution in the real form. Real form, I mean real number, as a real number. So now I can say case 1, if b squared minus 4c is positive, then y1 equals e to power r1x and y2 equals e to power r2x will provide two real solutions or real functions, real valued functions which are linearly independent. Linearly independent, and that's what we verified above. And the general solution will be of the form y equals c1 y1 plus c2 y2. So let's look at an example of this case. For example, let's say y double prime plus 5y prime plus y equals 0. Let's say solve y double prime plus 5y prime plus y equals 0 with y of 0 equals y prime of 0 equals 1. So here, what are the values for b and c? So here we can say that b is 5 and c is 1. So these are the values for b and c. And now we need to find the R1 and R2. Remember the solutions that we had were e to power R1x and e to power R2x. And R1 and R2 were basically the solutions of this equation here. The solutions of this equation, r squared plus br plus c equals 0. This equation is called characteristic equation of our ODE. Let me mention it here. This equation is called the characteristic equation of y double prime plus by prime plus cy equals 0. So once the equation ODE is given to you, you want to find the solutions. The solutions will be like e to power r1x and e to power r2x. What are those r1 and r2? They are these numbers. We found the expressions. But what are these numbers? These numbers are the roots of this equation, this algebraic equation, this quadratic equation. This quadratic equation is called the characteristic equation of this differential equation. So to find the characteristic equation of differential equation, just simply use the same coefficients. See, the coefficients here are 1, b, and c. We use the same coefficients 1, b, and c, but instead of derivatives, we use powers. So instead of second derivative, you use power 2. Instead of first derivative, you use power 1, and instead of zeroth derivative, you use power 0, which is 1. So here I can say that to find R1 and R2, simply find the roots of the characteristic equation of the characteristic equation of this ODE. And what is the characteristic equation of this ODE? So as we mentioned earlier, characteristic equation means we have to use the same coefficients. Coefficients are 1, 5, and 1. And instead of derivatives, we have to use the powers. Instead of the second derivative, we have to use power 2. First derivative, we have to use power 1. And zeroth derivative, just zero derivative means we have to use power 0, which is like r to power 0, which is 1. So then we will get r to power 2 r squared plus 5 r plus 1 equals 0. R squared plus 5r plus 1 equals 0. So this is the equation given to us. We use the same coefficients for 1, 5, and 1 to find the characteristic equation. Characteristic equation is not an ODE, it's an algebraic equation. In this case, because it's second order ODE, this is a second degree algebraic equation, which means a quadratic equation, just simply a quadratic equation. So to find R1 and R2, find the roots of this quadratic equation. So now find the roots of this equation, this quadratic equation. So R will be equal to -5 plus minus root 25 minus 4 divided by 2. So then this gives me -5 plus root 21 divided by 2. And maybe I can write it this way. That R1 equals -5 plus root 21 divided by 2. And R2 equals -5 minus root 21 divided by 2. And then y will be equal to, y1 will be equal to e to power r1x equals e to power -5 plus root 21 divided by 2 times x, and y2 will be e to power r2x. That's going to e to power -5 minus root 21 divided by 2 times x. So these are two linearly independent solutions for our equation. Two linearly independent solutions. And then the general solution will be of the form of y equals c1 y1 plus c2 y2. So that means y equals c1 e to power -5 plus root 21 divided by 2 times x plus c2 times e to power -5 minus root 21 divided by 2 times x. Lastly, to find c1 and c2, use the initial conditions. Y of 0 equals y prime of 0 equals 1. So that gives me, so y of 0 is c1 plus c2. c1 plus c2 equals 1. and y prime of 0. See, this is y. So at 0, it's just simply c1 plus c2, because see, if x is 0, then this will be e to power 0, which is 1. This will be also e to power 0, which is 1. And then I'll just get c1 plus c2. And what is y prime? We need to find y prime and then evaluate it at 0. Y prime will be minus 5 plus root 21 divided by 2 times c1 e to power minus 5 plus root 21 divided by 2 times x plus minus 5 minus root 21 divided by 2 c2 e to power minus 5 minus root 21 divided by 2x. So y prime of 0 will be minus 5 plus root 21 divided by 2 times c1 plus minus 5 minus root 21 divided by 2 times c2. And this has to be 1 as well. And then I have two equations with two unknowns. I can find c1 and c2. So from the first equation, I can say that c2 will be equal to 1 minus c1. So then I'll have a minus 5 plus root 21 divided by 2 times c1. So maybe I can call this number alpha 1 just for simplicity. Define alpha 1 as minus 5 plus root 21 divided by 2, and alpha 2 as minus 5 minus root 21 divided by 2. Then we'll have alpha 1 c1 plus alpha 2 c2. c2 is 1 minus c1. c2 is 1 minus c1. This has to be equal to 1. And then this means c1 times alpha 1 minus alpha 2. This is alpha 1 c1 minus alpha 2 c1. I can take c1 out, and then inside bracket I'll have alpha 1 minus alpha 2 equals 1 minus alpha 2, because this will be alpha 2 times 1 will be alpha 2. Take it to the other side, becomes minus alpha 2. And then c1 will be equal to 1 minus alpha 2 divided by alpha 1 minus alpha 2. This is the value of c1. And c2 will be 1 minus c1 equals 1 minus alpha 2, alpha 1 minus alpha 2. So this will be alpha 1 minus alpha 2 minus 1 plus alpha 2 divided by alpha 1 minus alpha 2. And then this will be alpha 1 minus 1 divided by alpha 1 minus alpha 2. This is the value of C2. And as we mentioned here, alpha 1, where alpha 1 is 1 minus 5 plus root 21 divided by 2, and alpha 2 is minus 5 minus root 21 divided by 2. And then the final answer will be y equals c1 y1 plus c2 y2. We found y1 and y2. We also found c1 and c2. c1 is 1 minus alpha 1 divided by alpha 1 minus alpha 2. y1 is e to power r1x. r1, I called it, here I called it alpha 1. Well, here I call them R1 and R2. So let me be consistent, and instead of because my alpha 1, alpha 2 are the same as R1, R2. So just to be consistent, let me leave them as R1 and R2. Because previously I called these numbers R1 and R2. So maybe I can say, instead of define, let me say note R1 is this number, R2 is this number. So we will have R1 C1 here, R2, and here R1 R2. And this one also R1 R2, and then this will be R1 minus R2 minus 1 plus R2 divided by R1 minus R2. And then the answer will be R2, R1 minus 1 divided by R1 minus R2. And this is R1 and this is R2. And final answer will be C1 Y1 plus C2 Y2. So that will be 1 minus R1 divided by R1 minus R2. 1 minus R2 divided by R2 minus R1 e to power R1x plus, then the second answer plus C2, which is R1 minus 1 divided by R1 minus R2 e to power R2x. So this is my final answer. Final answer of IVP above. IVP above. And here, basically, we can say that R1 is minus 5 plus root 21 divided by 2. R2 is minus 5 minus root 21 divided by 2. So there are some calculations involved, but the process was very simple. The ODE was given with constant coefficients. We found the characteristic equation by just using the same coefficients. And then we found an algebraic equation, in this case, quadratic equation. We solved that quadratic equation. We found the roots. We found the roots of that quadratic equation. And we found R1 and R2. In this case, these were the values. And then e to power R1x and e to power R2x were our linearly independent solutions. And the general solution was of the form C1 e to power R1x plus C2 e to power R2x. And then to find C1 and C2, we simply need to use the initial conditions. We use the initial conditions. Two initial conditions were given, two unknown C1 and C2. We found C1 and C2 in terms of R1 and R2. And then we substituted back and we found the final answer. All right, now let's look at the next case. So we covered the case where b squared minus 4c is positive. So case 2, if b squared minus 4c is negative, then the solutions of the characteristic equation r squared plus br plus c equals 0 will be r1 and r2 equals minus b plus or minus root b squared minus 4c divided by 2, which are complex numbers. So our goal, because in this course, we want to look at the real functions, real valued functions. Our goal is to write the solution in the real valued format. But right now it's written in a complex valued format. So first we want to maybe have a quick review about complex numbers, because maybe you haven't seen the basic properties of complex numbers before in any of the courses. And after that, we will use those properties to write the final answer in a real valued, as a real valued function. So we will have a review about complex numbers. And next, we will write the general solution in this case. As a real valued function. So let's have a review about complex numbers. So definition, let's start the definition. A complex number is a pair of the form alpha and beta, with alpha and beta are real numbers. So whenever you have a pair of the form alpha and beta, where first coordinate and second coordinate are real numbers, then you have a complex number. So the notation here is, so let me say denote the pair 0 and 1 by I. So I here is defined by the pair 0 and 1. So each so let me show on the plane. Let's say if you have the Cartesian plane. So 0 and 1 is here, which we can denote it with I. And what about the real numbers? Because we want the real numbers to be included in the complex numbers as well, because we want complex numbers to be a generalization of real numbers. We don't want to lose real numbers. So when we look at pairs, well, if you have a real number, let's say if you have a real number, so also a real number of the form, let's say a real number R can be written in the form R and 0. So see, we still will not lose the real numbers. Even we still have a real number, let's say R and R, we can replace it with R and 0. So R and 0 is considered as R. So replace R with R and 0. So in the set of complex numbers, whenever we talk about R and 0, we mean just simply the real number R. 0 and 1, we mean the complex number I. So in this, with this notation, any complex number any complex number. Remember, complex numbers are any pairs of the form alpha and beta. Any complex number alpha and beta can be written as so alpha and beta, we can write it as alpha and 0 plus 0 and beta. And then alpha and 0, we said that it's same as real number alpha. And then this one, I can write it plus beta times 0 and 1. And 0 and 1 means the complex number I. So we can write it as alpha plus I beta. So any complex number can be written as alpha plus I beta, where alpha is called the real part, denoted by real part of alpha plus I beta, and beta is called the imaginary part. Imaginary part denoted by imaginary part of alpha plus I beta. So alpha is called the real part, denoted by real alpha plus I beta. Beta is called the imaginary part, denoted by imaginary part alpha plus I beta. This is a general form of a complex number, alpha plus I beta. Alpha is called real part, beta is called the imaginary part. Now let's look at the operations on complex numbers. What type of operations can we have on complex numbers? Operations on complex numbers or between complex numbers. So first, addition. Let's say if you want to add two complex numbers, let's say alpha 1 plus I beta 1 plus alpha 2 plus I beta 2. So this one is defined as alpha 1 plus alpha 2 plus I times beta 1 plus beta 2. So addition of two complex numbers is very simple. You just simply need to add the real parts together, add the real parts together, and add the imaginary parts together. That's how you will add two complex numbers. And then the second operation is multiplying with a scalar. So scalar, so second condition or second operation, multiplying a complex number by a real number, let's say by a real number. Let's say C times alpha plus I beta. This is defined as C alpha plus I C beta. Here C in R is a constant, a real constant. So if you want to, for example, multiply a complex number by 2, you just need to simply multiply the real part by 2 plus multiply the imaginary part by 2. Very simple. And then we can also multiply two complex numbers together, multiplying two complex numbers let's say alpha 1 plus I beta 1 times alpha 2 plus I beta 2. So how can you multiply two complex numbers? So the way that we are going to define this alpha 1 plus I beta 1 times alpha 2 plus I beta 2, we can define it as alpha 1 alpha 2 minus beta 1 beta 2 plus I times alpha 2 beta 1 plus alpha 1 beta 2. So where is this definition coming from? This definition basically comes from the fact that I squared, we want to define this multiplication in a way that I squared to be minus 1. Because we want a generalization of real numbers, a generalization in which, let's say the equation x squared equals minus 1 has a solution, because x squared equals minus 1 has no solution in real numbers. But if you want to have x squared equals minus 1 to have a solution in this generalization called complex numbers, we want some number to exist such that, a square of that number is minus 1. So that number is basically I. We want I squared to be minus 1. So if I squared is minus 1, and if you expand this, see, if you expand, you get, for example, alpha 1 times alpha 2 plus I beta 1 times I beta 2. See, if I expand this, I'll get alpha 1 alpha 2 plus I squared beta 1 beta 2, and then alpha 2 beta 1 I plus alpha 1 beta 2 I, and I squared is minus 1, so alpha 1 alpha 2 minus beta 1 beta 2, and plus I times, take out I out as a common factor, and then I'll have alpha 2 beta 1 plus alpha 1 beta 2, which is what I wrote here. So if you're wondering where this definition is coming from, it comes from the fact that I want to define this generalization in a way that I squared is minus 1. And if I squared is minus 1, and then this is how I have to define this definition. So this is where this definition is coming from. But let me leave this as a definition here. And in particular, we can say that I times I is equal to minus 1. Because when you want to multiply I with I, that means alpha 1 is 0, beta 1 is 1. So if I replace alpha 1 with 0, beta 1 with 1, and same for alpha 2 and beta 2, then alpha times alpha 2 will be 0, minus beta 1, beta will be minus 1. This guy will be 0, this guy will be also 0. The answer will be minus 1. And this means that I squared is minus 1. So that means, so we defined the complex numbers and operations between them in a way that x squared, that the equation x squared equals minus 1 has a solution in the set of complex numbers. So x squared equals minus 1 had no solution in the set of real numbers. But x squared equals minus 1 now has a solution in the set of complex numbers. Because I is a solution for x squared equals minus 1, because I squared is minus 1. I satisfies the equation x squared equals minus 1. So I is a solution for x squared equals minus 1. So that's already a success, that we could generalize the concept of real numbers in a way to a set called complex numbers in a way that x squared equals -1 has now a solution in this new set, in the set of complex numbers. Now, because I is a solution for I squared equals -1, I is also denoted with root -1, because I squared is minus. We just verified that I squared is -1. So we can also denote I with root -1. So it has a solution with the set of complex numbers, namely I equals 0 and 1. For this reason, I is also denoted by root -1. So we can say that any complex number can be written as alpha or z equals, usually the notation that we use for complex numbers, the letter that we use is z. Z equals alpha plus I beta, where alpha equals the real part of z, beta is equal to imaginary part of z, and I is equal to 0 and 1 equals root -1, and I squared is -1. So this is basically what we have said so far about complex numbers, that any complex number can be written in this form, and these are the basic notations and properties of complex numbers. So let's look at an example. Let's say if you want to evaluate, for example, let's say 2 plus 3i times 4 minus I. So solution 1, which I can leave as exercise, we can try to use this formula here that we introduced as a definition of multiplication of two complex numbers. So we can use this formula here because here we provided a recipe to calculate alpha 1 plus I beta 1 times alpha 2 plus I beta 2. And here you have alpha 1, alpha 2, beta 1, and beta 2. So let me leave this as exercise. Use formula or definition 3 above for multiplying two complex numbers. But let me do it with solution 2, is with expansion and using the fact that I squared is -1. With expansion using the fact that I squared is -1. So here we have 2 plus 3i times 4 minus I. So if I expand it, 2 times 4 minus 3 times I plus 4 times 3i minus 2i. So that becomes 8 minus 3i squared plus 12i minus 2i. And we know that I squared is -1. So then I'll get 8 plus 3 plus 10i. And this is 11 plus 10i. So the answer is simply 11 plus 10i. We just needed to expand and use the fact that I squared is -1. Now let's look at another example. Let's say if you want to evaluate evaluate 3 plus, or let me write, not evaluate, write 3 plus I divided by 2 minus I in the form alpha plus I beta. So this is written of the form, let's say alpha 1 plus I beta 1 divided by alpha 2 plus I beta 2. But we need to write it in the form of alpha plus I beta. So to do that, we need to know about the concept of conjugate of a complex number. So to do that, we will define the conjugate of a complex number as follows. The definition, let Z equals alpha plus I beta be a complex number. The conjugate of Z denoted by Z bar is defined as follows. Z bar is defined as alpha minus I beta. So conjugate of complex number is found easily. We just need to change I to minus I. Just change I to minus I, and then the new complex number is called conjugate of the original complex number. Now, what is the important property of a conjugate of a complex number? So important property of conjugate of a complex number is that, you know, Z times Z bar, let's see what it is. Z is alpha plus I beta. Z bar is alpha minus I beta. And then if we expand this, then we get alpha squared minus I beta, I squared beta squared plus I alpha beta minus I alpha beta. So these two cancel. And then we'll get an I squared. We know it's minus 1. So we get alpha squared plus beta squared. And alpha squared plus beta squared is norm Z squared. So norm Z is defined as root of this number. So Z times Z bar is alpha squared plus beta squared, or maybe I can write it here that. And so far we showed that Z times Z bar is equal to alpha squared plus beta squared. And alpha squared beta and alpha squared plus beta squared, let's say, and root alpha squared plus beta squared is defined as norm of Z. Norm of Z denoted by norm Z. So maybe you have seen in vector calculus, basic vector calculus, or even in physics, that if you have a vector here, let's say alpha and beta, then as a vector, here we are denoting with Z. Maybe in physics you denote it with V. Then the norm of this, or the magnitude of this, is denoted by norm Z, and has the value root alpha squared plus beta squared, according to Pythagoras, right? The length, this length here, denoted by norm Z, has root alpha squared plus beta squared by Pythagoras. So we showed that Z times Z bar is alpha squared plus beta squared. And root alpha squared plus beta squared is defined as norm z, which is by Pythagoras, this length here. This length here is root alpha squared plus beta squared divided by norm z, and z times z bar is, therefore z times z bar will be norm z squared, because root alpha squared plus z beta, root alpha squared plus beta squared, you are saying it's norm z. So alpha squared plus beta squared will be norm z squared. So important property of complex conjugate is, so with this notation, the important property of complex conjugates is z times z bar is equal to alpha squared plus beta squared equals norm z squared, where z is equal to alpha plus I beta, and norm z is defined as root alpha squared plus beta squared. So when you multiply a complex number by its conjugate, you get a real number as a result. See, this is the number I has, the complex number I has disappeared here. In the original number z, we had I, alpha plus I beta. But when I multiply with z bar, I will disappear, and z times z bar becomes alpha squared plus beta squared. So if I go back to the example here, I want to make sure that this denominator, I in denominator disappears, because if I in denominator disappears, then I will have a number of the form alpha plus I beta. How can I make it disappear? By multiplying with the conjugate of it. We just saw that if I multiply a complex number by its conjugate, then the imaginary part will disappear. So we just need to multiply top and bottom by conjugate of denominator to make sure that the imaginary part of denominator will disappear, and then I will have a number of this form. So now back to example above. Writing, what was it? 2 plus 3 plus I over 2 minus I in the form alpha plus I beta. So let's multiply. Let's multiply and divide by conjugate of 2 minus I, which is 2 plus I. How can I get conjugate of a complex number? It's very simple. Just simply replace I with minus I. So conjugate of 2 minus I will be 2 plus I. So then I will have 3 plus I divided by 2 minus I equals 3 plus I times 2 plus I divided by 2 minus I times 2 plus I. So this becomes, if I expand, 6 plus I squared plus 2I plus 3I is 5I, and denominator I will have 4 minus I squared. And then this will be, so I squared is minus 1. So 6 minus 1 plus 5I divided by 4 plus 1 minus I squared, but I squared is minus 1. So 4 minus minus 1, which is 4 plus 1. So this will be 5 plus 5I divided by 5. The answer will be 1 plus I. 5 divided by 5 is 1. 5 divided by 5 is 1. So 1 plus I. So we wrote 3 plus I divided by 2 minus I in the form alpha plus I beta. Okay, guys, so these were some basic properties of complex numbers, the definition, the basic operations, such as multiplying two complex numbers and also conjugate of a complex number. That was very simple, just simply replace I with minus I. And the conjugate of a complex number has the property that when you multiply a complex number by its conjugate, z times z bar, you'll get norm z squared. The imaginary part will disappear. And you just get the magnitude of that complex number raised to power 2. Okay, guys, so next time we will look at some more properties of complex numbers, such as Euler formula. And then after we finish the review for complex numbers, we'll go back to the topic of differential equations to see how we can write the solution of the ODE in the case of discriminant b squared minus 4c is negative. How can you write the solutions as a real valued function? Okay, guys, so that's what we'll do next time. So thank you and see you next time.